So I want to talk today about computational design, my journey through almost 40 years at SOM involved in computational design, how they affect my process, and the examples of things that I've done in computational design. Computational design is not a new field, and maybe the name is fairly recent, and it's not necessarily dependent on computers. So the work shown here was done by architects who probably have never used a computer or seen a computer, but I would still call the result of their work and the way that they did it computational design. It's a process involving logic, geometric rigor, inspiration from science fields like physics, chemistry, biology, structural concepts, materials, and more. Darcy Thompson, images of sort of inspiration from nature, examples. Darcy Thompson demonstrated relationships among creatures based on their morphology and how growth and form are related to environment and structural considerations. And a more recent example of a similar application of nature to computational design is in the work of Neri Oxman. Horace Lovani, who was my professor and mentor when I was at Pratt Institute, applies concepts of morphology and genetic coding to organize and categorize forms, and even discover new forms using this method, and applies these concepts to fabrication techniques also. Particularly focused on relationships between forms, this geometric thinking was my introduction to concepts of computational design thinking, and exploring forms in 3D as well as 2D. Walter Netsch was a former design partner at SOM, and he developed an approach to design that he called field theory, a highly versatile approach to the geometric generation of architectonic structures intended to be uniquely suited to their purposes and environments. A focus on geometry and considerations of systems is very evident in his work. Another example of Walter Netsch's work, a great example of a strong focus on geometry, and maybe some origami as well. So in the 1970s and 80s, SOM created their own system for design, software for analysis, design, and documentation. As you might know, SOM is a multidisciplinary and intensively collaborative and firm designing large and complex projects. The software was designed to reflect that culture and also encourage it, with an interest in design strongly influenced by geometry, nature analysis, and having started to discover the potential of computers when I was at Pratt Institute in the 1980s. Applying this process of computational design thinking to some of the real projects we were doing at SOM was very exciting to me, and it still is. Originally used on mainframe-like computers, the computers required special rooms and maintenance. In 1980, SOM published a little brochure, like an 80-page booklet, showing some of the examples of what we were using this system for. This was published in 1980, so a lot of the development work and use of these tools was already in place. We also created a video, in this case also a showcase video like the brochure. We had offices in 9 cities, and we created a fly-through of each of the 9 cities. And here's a segment of that fly-through focusing on New York. So the quality is very poor, but this was done in 1980. And in fact, we're looking at it on a machine it really wasn't designed for. The terminals that we were using were not pixel-based terminals. Right? They were Evans and Sutherland machines, so they were vector-based. SOM system was eventually able to be used on PCs. As PCs were becoming more available, we ported the system to be able to be used on those machines. As powerful tools become more available, even ubiquitous, it's easy to overlook contributions to the field of early developers and early adopters. In addition to design, we also created tools for analysis. So the analysis example on the bottom right was to create a no-shadow envelope for a site in Boston. There was a law being passed that said we're not allowed to cast any new shadows. So we had to create a tool that would analyze the site and the existing conditions and create a mesh that would not cast any shadow. We had already begun designing, so you could see where we would have failed, and we had to go back and redesign, in fact. Even software, and this was done using our original software, our self-designed software, evaluating massings for compliance with New York City zoning. One of the things that I love about SOM is collaboration. And what is the most collaborative activity? And I would argue that it's chamber music. Even more than in an orchestra, chamber music players need really to interact with each other. And what each player does informs what the other players in the group do as well, right? They influence each other. A friend of mine is a sculptor, and I was recently talking with him about collaboration. He actually brought up the topic, and he talked about collaborating as a sculptor, who usually we think of as working alone, collaborating with the materials that they were using, and also with the tools that they use. And I immediately saw a connection to the work that I do, where often I'm working alone, although I'm collaborating with people at the office and with teams. I'm often sitting behind a computer, working on a script and working on a model. And those are the things that I'm also collaborating with, right? Often when I'm working on a script, I get inspired by the script as I'm writing it, and it helps push me forward. The goal and outcome are the results of my work, and others in our group, and many of us, in fact, as well, is often not a single design solution, at least not immediately, but a system of solutions or a design space which meet the design criteria. It's easy, and maybe easy is not the right word, to visualize and communicate a final design, but to visualize and communicate a system of designs, a design space, is maybe not so easy. So several techniques have been developed. We can see what the different parameters look like, what might be the optimal form. We don't see the forms themselves, although with Design Explorer, we might get a hint of it as we select different lines in the multi-axis plot. Another tool that we might use to visualize a design space, but where we actually see the models in the space, is this system using higher dimensions as a structure for the design space. And this method was developed also by Haresh Lalvani, and this is some of the work that I was doing with him at Pratt and afterwards as well. While discrete models are shown at the vertices of these underlying structures, each system actually represents an infinite collection of models, of possibilities. And as parameters fall between vertices, along the edges of the lines or in the faces of some of these higher dimensional structures, there's an infinite set of possibilities as the parameters are changing, say, from 0 to 1. Another design space visualization that I did recently for a project at the office is for a set of fins on the facade of a building. So we ran a daylighting analysis of various desk locations within the building, and looked at the length of the fins and other parameters that define the fins, their angle, their spacing. The main chart shows lux values on the desk that we selected in the top left. And as we change any of the parameters, as we change the length of the fins, and you could see that change happening here, or any of the other parameters, we see the results of the analysis. A couple of project examples. This was for a competition for a tower in Seoul. We explored primarily variations of the diagrid structure. SOM's self-created computational system always included the ability to script. And when I started using it, that was one thing that fascinated me about the tool, that I was able to control it in a way more powerful than just typing commands in the system. Most people didn't actually use that capability of the tool. Most people were not so comfortable scripting. It also requires, I think, in addition to learning the scripting language, which was pretty simple, I think a way of thinking about designing in order to be able to design that way, to use a script to design. Eventually, we stopped using our own system and we started moving to more available tools. The first one that we moved to was AutoCAD. And when we started using AutoCAD, I wasn't ready to give up this method that I developed using scripting as part of my design process. So I learned how to script in AutoCAD using Lisp, AutoCAD scripting language. My first introduction to more interactive and visual tools designed to be used by architects and engineers and computational designers was at Smart Geometry, at a Smart Geometry conference in 2006 in Cambridge, England. We were using Bentley's generative components, and this is an example of that tool. You know, before I went to this conference, I knew there must be other people out there who had similar feelings about design and similar skills, maybe in scripting, using different tools, but I had never met any of them. And at this conference, I finally got to meet people who were working in a way that was similar to mine. And I met many new colleagues and friends that I still keep in touch with today. Many of them are here, in fact. During the competition and the concept design phase of this project, there was a close collaboration with the design team and engineers, especially focusing on the design of the diagrid. And as we moved through design and construction documentation phases, we used many different tools, including Rhino, including Excel, including Digital Project, and ultimately even Revit. And we developed this concept of the master model, and even a couple of people at the firm, Kat and Nick Holt, wrote a paper about this concept as it applied to this particular project. Another project was the World Trade Center. And like Lotte, like the previous example with the diagrid, I was actually embedded in the design team for that project and for this one as well. And one of my primary responsibilities for this project was to work on the spire of the building. We began work on the project in late 2001, and we're still using our system, which was called AES. And not long after that, we started using AutoCAD. So much of the scripting that I used to implement all the parameters and the variations in the design of the spire was done with scripting in AutoCAD. Initially, it was a lattice-type system, like you see on the lower left. We were also studying lighting, in addition to so many other aspects. Eventually, we decided to use a panelized system, mostly for structural reasons. But after wind analysis, we discovered that even the panel system was not stiff enough, right? The spire moved a little bit too much. So we had to add these helical strakes, these helical fins that go up around the spire. And we actually thought it was visually interesting. And not only that, but it's dynamic. So these two images are identical, except different times of the day. So as the sun moves, these helical strakes create interesting shadows. For an earlier design of this same building, the World Trade Center, as I was working on the facade, I ran into a trigonometry problem that I thought was very simple. And I was figuring out how can I script this to become part of the design process to build this model. And I was spending so much time just trying to figure out the variables that I needed, A and B, and X. If I figured out one, I'd be easily able to figure out the others, but I wasn't able to figure out any of them. And usually I'm pretty good at solving simple trigonometry problems. But I was so embarrassed have to send an email to one of our engineers to help me solve this. And this is what he sent back. So I didn't feel quite so bad after I got this. And then was able to implement his formula into the Lisp script that helped me generate the models. Some examples of projects that really express the collaboration between architects and we call them structural designers, actually, our engineering team. This is a project that we did at Penn Station. And it's a small project. It's a canopy that leads to the subway entrance at Penn Station. And one of the computational designers in our group, in the computational design group, worked closely with one of the structural designers on developing the form using tools like Kangaroo. To optimize the shape of the structure. Another project was the Hangzhou Center. This animation illustrates the various aspects of the computational design projects for this project, computational design process for this project. It was an integrated workflow with many different people on the design team contributing to the computational design process. And the rigor of this process with computational design techniques allows geometrically complex projects to be well documented and able to be constructed. So the building is, I think, just recently completed. As you may have guessed from earlier slides, patterns is a strong passion of mine. So here we were exploring a non-periodic pattern in response to a design request from the project team for this competition for a roof. So we applied that pattern to the roof. So you don't perceive a grid, it's non-periodic, and it lets light through, almost like light coming through leaves in a tree canopy. But it still has the strong geometric rigor that's in all of the projects that we work on. So I call this section What's Next, but a lot of it is really what's happening now. So in collaboration with the structures group, and these were done mostly by the structures group, created these pavilions, these vaulted pavilions, that use methods that are not new also, right? Methods in history using graphic statics, right, from the 1840s or 1860s. The image on the right is a pavilion, a glass vault that was constructed in London just as the pandemic was starting. So unfortunately, many people didn't get to see it at the exhibition, but you can see it now. So a few interesting things about it. It's a doubly curved vault made out of glass, right? So the geometry of the vault allows the system to stand up, and it's created precisely using two robots that work in coordination with each other. Another recent project was a collaboration with the European Space Agency and the Aeronautics Department at MIT for this Moon Village. The intent was to design a habitable structure for anticipation of people going to the moon, not just astronauts, but regular people, and spending some time there. How can we create an environment that's comfortable and satisfies all the requirements for being on the lunar surface? For many years, we've been collaborating with academic institutions and others, including RPI, their CASE program, Michigan's Taubman College of Architecture, and others, including industrial partners like Prometheus, who's developing the biobricks that you see in the lower left. So these collaborations result in a lot of research and ideas, thoughts that ultimately, hopefully, make it into some of our projects, like the one in the upper right. The stereo slab is an example of one of these research, where we're optimizing material and structure and being able to fabricate the complex formwork that's required to cast these. And this is just the pavilion, but how can we expand that to become part of much larger structures as well? mathematicians often use the term elegant to describe an equation that's simple, that's beautiful, that performs in a particular way. And I think there's a new beauty that we're beginning to appreciate in architecture, which is the result of this rigorous geometric and structural process. Urban Sequoia, which was initially unveiled at COP26 in 2021, is sort of a culmination of many facets of this research, including architecture, engineering, sustainability, materials, building systems, and others. And while using innovative concepts and techniques and tools, this project could actually be built today, tomorrow. And in addition to getting people at the office excited about using computational tools and computational design thinking, I've also been teaching computational design over the last decade or more, most recently up at City College. And my primary focus in teaching about the process and thinking aspect of computational design is foremost, right? We talk about how do you think, how do you develop strategies for solving problems? And then the tool is really second. So the class is a grasshopper class, right? So after we learn some of the strategies and geometry and other concepts that I think students should be aware of and use in their design processes, then we start to learn how to use tools like Grasshopper to apply these concepts. And who knows, in 10 years, maybe we'll be using different tools. Maybe it won't be Grasshopper, but the students will still have the ability to think in a way that will allow them to apply these concepts to any tools. I'm always excited to share what I do with my colleagues at the office, with students, and today with all of you as well.